Okay.
I just wanna mention
You
that.
had a question?
No, I was watching the recording of the
Mhm.
weekend and then someone on the recording was like trying to get your attention for questions, but you can't hear.
Online?
Who are online.
Oh, yeah, somebody
He
was,
hello?
he was like, Shannon.
Oh.
So I don't know if there's like a way to. keep-
Wait, really? That's not good.
Yeah, that was
I mean,
So loud.
Yeah, he was kind of screaming though. I was like,
well, if this person is watching the recording again, I'm sorry. Like, I could not hear you at all. But right now, technically, I should be able to hear you. So the only one who's online is Francesca. So hopefully, if anything, just write something on the chat. Oh, someone's gonna see it eventually. So yeah, that's why it's better for you to come in person rather than online. So either way, whoopsie dipsy. Let's talk about multiplicity and splitting. Okay. So this should be a review from Orgo 1, and hopefully you guys learned this back in lecture. So for multiplicity slash splitting, remember they mean the same exact thing, but we use a specific formula, right? What's the formula that we use? n+1, what does the n represent? Any neighbors. Okay, now for the neighbors, there were some requirements. What are some of the rules to find neighbors? The neighbors have to be within 3 bonds away, which means that they can be 2 bonds away, they can be 1 bond away, okay? It doesn't mean that they have to be 3 bonds away every single time. Now, what about heteroatoms? Can I go through them? Heteroatoms.
Is that like the oxygen? No.
You can go through them. Heteroatoms are oxygen, nitrogen, anything that's not carbon or hydrogen. Yes. If it's second writing, that's okay. I get it a lot. Do you guys remember hearing that in class? The 6 bonds away? Was it a specific example or?
He's talking about like complex.
Okay, complex multiplicity is something different. Right now, we're in normal multiplicity, which is something that you learned in Orgo 1. So right now, we're just focusing on 3 bonds away, n+1, simple as that. We're not going past any heteroatoms. Again, heteroatoms are anything that's not carbon or hydrogen. Now, splitting or multiplicity. We find that in HNMR for sure. Now, what about CNMR? Do we see it? No, remember, that's the main difference between those two. In CNMR, you're never gonna see splitting. No, yes.
When do you define, heteroatom can't go through the n+1?
For example, if we have this molecule and we have an alcohol group in here, let's say I want you to find the multiplicity for that hydrogen. So I'm going to count the 3 bonds away. 1 bond away, I touch an oxygen. So automatically I can go past it. So that's what I mean.
One,
It's going to be 0 + 1, which gives you a singlet.
okay.
Okay. Okay, there's another person. Okay. So let's go through this. I'm gonna walk you guys through the first problem, so we're all clear on the rules for multiplicity. So just for this case, let's go right to left, okay? I'm gonna start with this hydrogen in here. What functional group is that?
Aldehyde?
Aldehyde. Yes, you guys still have to remember those names, so please do not forget about those guys. Okay, so to find multiplicity, what I like to tell my students is that you're always gonna start by hugging your hydrogen from the signal you're looking at. That's why I circle that specific hydrogen. Yes. Thank you. I have to fix that, so yeah, it's just gonna be for today, hopefully. But either way, okay, we're gonna start by hugging that hydrogen, and then we just count the bonds away. 1 bond away, I touch a carbon, right? Now, this is the point where I start branching off. Remember that you have to go through each of those possible branches. If I go up, I touch an oxygen, there's nothing up here. Okay, no neighbors. But I can go to the left. 2 bonds away, carbon, right? Now, 3 bonds away, I touch 1 and 2 hydrogens. Because they're part of a different signal, those are going to be my neighbors. So 2 plus 1 gives you what kind of multiplicity? What's the name? Triplet. Beautiful. Whoops. Let's redraw this guy. Okay, so far, questions on how to use the 3 bonds away rule. Usually that's the tricky part. Yes. Yes. You can stop right there.
Please stop where there is a hydrogen.
Mm. Yes. Okay, now, next signal is gonna be your hydrogens in here, right? Same process. I start by hugging either of those hydrogens, 1 bond away, carbon 2 bonds away, carbon 3 bonds away. I touch 1 neighbor to the right. On the left side, if I repeat the same process, do I have any neighbors? How many? 2. So that means I have a total of 3 neighbors, which gives you what multiplicity? Quarter. Now, we repeat the same exact process in here. Now, without showing you the bonds away, what's going to be the multiplicity in that case? Do we all agree?
So the last example, quartet, why is it 3 neighbors? It's 1 and then the hetero atom.
There's 1 neighbor. Again, we're looking at the signal, right? Okay, so to the right, we only found 1 neighbor because if we go up, we can go past the oxygen plus there's nothing else. Now to the left side, remember, we have to repeat the same exact process. 1 bond away, carbon, 2 bonds away, carbon, 3 bonds away, I touch those 2 hydrogens. That's why I have a total of 3 neighbors. And now, in this case, we also said that this guy was a quartet, which you guys are absolutely right. Do you guys need me to show you the neighbors? Yes, that's okay. Okay, so same process. 1 bond away, carbon. 2 bonds away, carbon. 3 bonds away, I touch the 2 hydrogens in the pink signal. So far, 2 neighbors to the right. If I repeat the same process to the left side, 1 bond away, carbon. 2 bonds away, carbon. 3 bonds away, 1 little hydrogen in there, which makes it a total of 3 neighbors. Okay? Questions on that? We're good?
Counting neighbors from both sides.
Yes, you have to branch out in every possible way. Okay, now what about the little baby hydrogen in here? How many neighbors does it have? We got 8 neighbors?
Yeah, so it's
Oh, they have to be within 3 bonds. So if we just keep expanding, that's going to be 4 bonds away or 5 bonds away. This one. Because again, we're on the red one, right? Let's show it with this. Okay, so again, we're looking at the hydrogen here. 1 bond away, carbon. 2 bonds away, carbon. 3 bonds away, that's when we touch our 2 neighbors in here. Now, if we repeat the same process and keep going to the right. 1, 2, 3. I still have to stop at 3, and I still touch a carbon. So it doesn't make sense for me to keep going since I'm not going to reach any other hydrogens. Okay? So that's still a valid question. A lot of students get the same question. Okay? So does that clarify things for you? A little? Okay. Okay, what about the little hydrogen here? I heard 8. Do you all get 8?
Wait, okay, I thought 8, but then if we branch out to the right, 1, that's carbon, and then get those 2 at the top, but then if we branch out down, oh no, but then that's a carbon, no.
Okay, let's do this one. Let's walk through this one. Okay, so hopefully you can see the ones that are in the method groups. They're of course gonna be neighbors, okay? Because 1 bonds away, carbon, 2 bonds away, carbon, and then I'm able to reach all 3 hydrogens in both method groups. Okay, so far 6. Now I have to cover the right side. 1 bond away, carbon. 2 bonds away, carbon. 3 bonds away, if I go up, I touch 1 and 2 hydrogens. If I keep going right, I touch carbon, so I have to stop right there. So that does give me a total of 8, which is going to give you technically a noned. But for this class, usually whenever we reach either a quarter or a quintet, we just start calling it a multiplet, okay? Just to simplify it. Or multiplet.
You said you have to stop. when you got
Because
to-
remember our rule, 3 bonds away max.
That one, can you count the bonds again for like
Yes.
how far they are from each other?
Okay, so again, 1 bond away, carbon. 2 bonds away, carbon. 3 bonds away, I touch a carbon. I already reached my limit from the rule. Okay, now, what about the last signal, the one with the methyl groups? How many neighbors do they have? Just one neighbor? Why can't the ones at the bottom be neighbors? Because they're, no, it's not because they're too far, it's because they're the same exact signal. Remember, hydrogens of the same signal cannot be neighbors of each other.
Wait,
So,
there's the same signal, because they're both methyl groups?
so in this case, hopefully you guys remember that single bonds constantly rotate. So in this case, let me erase some of this. So, whoops. This bond is going to be constantly rotating, meaning that both methyl groups in here, they're both going to be exposed to the same exact environment, meaning that they're the same signal. Therefore, they can be neighbors of each other.
And if they were a double bond, then they would be.
In this case, yes. Okay, any other questions on the first molecule? Do you all get how to use the 3 bond rule away? Yes.
For the little hydrogen, you just counted up the eight, hydrogen surrounding it plus the one, right?
Okay, now I'm gonna give you guys 5 minutes to try and figure out the number of signals for HNMR and the multiplicity for each one of them for the next 2 molecules. Okay, take 5 minutes, try to do it as fast as possible. And then if you have any questions, just raise your hand. Okay, so hopefully we all finished finding the multiplicity for the signals. If you didn't, that's completely okay. I just gave you 5 minutes. So let's look at the molecule in the middle. Okay, so first of all, how many signals did you guys find in total?
For the entire molecule or for each section?
For the entire molecule?
I thought it was 6 left. Right.
No, no, no. How many signals did you find?
I believe.
Did you find 2 signals? Did you find 5 signals? Okay, I heard 6. Did we all get 6, 7, 8,
I got
6, and 8? Okay. So technically, you are both correct. So let's explain this. So let's go through the easy ones, which are the ones on the left side. So the ones in your dear method groups, those are the easiest ones to spot. Because remember, single bonds, they constantly rotate, they're exposed to the same exact thing. Now, what's the multiplicity for that signal? It's a doublet because my only neighbor is the little baby hydrogen in the junction. Now, what about this one over here? Signal number 2. It's just going to be a multiplet because anything that's higher than a quartet, we're just going to call it a multiplet. Okay, we don't have to be so precise. This one is 6 neighbors, 6, 7, 8. 8 neighbors in total. So 8 plus 1, non-net. So yes. So 1 bond away, carbon. 2 bonds away, carbon. 3 bonds away, I'm able to reach all hydrogens in here. So that means that I can also reach the ones at the bottom here, which makes it a total of 6, but repeat the same process to the right. 1 bond away, carbon. 2 bonds away, carbon. 3 bonds away, 1, 2.
But I thought, at the branches, they were the same signal, so we still count them as neighbors. So they're like.
Yes, as long as they're not part of the same signal, you're going to count every single hydrogen from a different signal.
But I thought they are the same.
The method groups are the same signal, but again, we're looking at the multiplicity of this guy. That signal is not the same as the one in the method groups. That's why they can split each other. Okay, now this one, signal number 3. How many neighbors did you guys find? Doublet, triplet? And you're absolutely correct for a doublet. 1 bond away, carbon. 2 bonds away, carbon. 3 bonds away, I touch the little hydrogen over here. If I repeat the same process to the right, 2, 3, I touch carbons, no hydrogen, so no neighbors to the right. Okay. Now, what about the hydrogens in here? How many neighbors? What's the multiplicity? Triplet, which means I only have 2 neighbors, which are 1 and 2, right there. Okay? Yes.
The neighbor of itself, right? Like, for example, that group, like.
Like this one is a neighbor of the one on the right? No, because they're part of the same signal. Okay, now the hydrogens in here. How? Triplet. Same process. 1 and 2 neighbors. Okay, pretty simple. Now, I heard some people saying 6 signals in total or 8 signals in total. If your professor were to say that all signals are separate from each other, or if he were to ask you for the theoretical number of signals, then you're going to be grouping these 2 guys together. So these ones are going to be, whoops, I didn't label the other ones. 4 and then 5. These 2 would be 6. Then we would have 7. And then we would have 8. But what you're going to see in practice and in most of the problems with spectrums is that all of the hydrogens in your benzene group are grouped together. Okay, so all of those are just signal 6. And as far as the multiplicity goes, is that every hydrogen you see in your benzene group is just going to be showing a multiplet. Because all of those multiplicities that you see in each of those signals, theoretically, we're not going to see them as separate in the spectrum. They're all gonna be so clustered together, there's not gonna be a difference between the signals, okay? It's only one signal, yes. Again, unless your professor says that you can see all of the signals separate from each other. Okay, questions in the second molecule? Very good. Which hydrogen? Six would be a 1, 2, 3. Yeah, 6 would be a doublet, 7 would be a triplet, 8 would be triplet. Yes, in theory,
So it's 6 signals.
yes. Because all of the ones in the green portion, they're grouped together. The other one was, yes, 1, 2, 3, 4, 5. 5 signals in total. And then,
What is it? Oh, no.
because in practice, we're always gonna see the hydrogen part of the benzene group just clustered together.
So they're not stateless.
No. They're just multiplets. Question? There's 5. So in this case, when we were doing the theoretical multiplicity, technically we were splitting the benzene right in half, like over here, right? Okay, so because these two guys are practically at the same distance, I grouped them together. So far I have 2 hydrogens in my benzene group. Then these two guys are also grouped together. That's where we have our 4. But also this little hydrogen that you see in here, the one that's being split through by our symmetry, that's still gonna count as a hydrogen. It's still there, it's still present. So every single hydrogen you see somewhere, it's gonna count, okay? Okay. Any other questions? Yes. So that's just because in practice, we're always gonna see them grouped together. You don't have to do the 3 bonds away for any benzene groups. Mhm. This is just something that you're gonna see in practice and in lab if you're taking it. Okay. For this molecule, do we have any planes of symmetry? How many? Only 1. Exactly, right in the middle. Now, how many signals did you guys find? A total of 4. Beautiful. So the ones in your method group, that signal 1, what was the multiplicity you found? Doublet. I forgot about this little baby hydrogen. But that guy, what's the multiplicity? Multiplet. 2 hydrogens in here, signal 3. Quartet. Doublet. And then last ones in here. What are they? Singlet. What about the 2 hydrogens in here? Why can they be neighbors of the last signal? Because they're the same signal because of the symmetry.
Why?
Mhm.
Oh, wait, oh.
Because remember, there's a plane of symmetry right in the middle, meaning that these 2 guys, whoops, are signal 4. These guys are signal 4. Signal 3 is also mirrored in here. This is signal 3. Signal 2, baby hydrogen in here. And then we have our method groups, which are signal 1. Because remember, again, planes of symmetry, we get the same exact thing in both sides. Okay?
How does it work again on that number 4 for the singlet? Like, I don't understand.
Okay, so let's look at this guy. I start by grabbing that hydrogen, 1 bond away, carbon. 2 bonds away to the left, carbon. 3 bonds away, carbon. No neighbors to the left side. We repeat the same process to the right, but if we do that, 1, 2, 3, I touch hydrogens. But remember that we found the plane of symmetry beforehand. So they're the same exact signal. Hydrogens of the same signal, they cannot be neighbors of each other. Okay. Okay. Any other questions on the 3 molecules we just covered in here? Okay, hopefully that clarified a lot of the questions you had in lecture. If it didn't, just raise your hand. I'll try to re-explain it. But let's move on to the next concept. Now, your professor is usually known for having a really specific phrasing of the questions, okay? Like that one in there. Determining if the following molecules would show HH spin-spin splitting. That's a mouthful. What does it mean? This guy in here.
Whether the electrons, the protons are going opposite or the same.
You would think so because it says spin-spin. So no, it doesn't really have to do with the spins as far as you guys should be concerned. If you're taking upper chemistry classes, then it would be good if you guys know. Personally, I do not know the exact scientific reason, but basically, whenever you see that wording is that they're asking you which of the following molecules show something more than just a singlet. So if a molecule has 2 signals and they're both singlets, we're not showing spin-spin splitting. But if I have a molecule with 2 signals and one of them it's a doublet and the other one's a singlet, that one is showing spin-spin splitting. So molecule has something higher than a singlet. Okay.
It doesn't just have to be doublet, it could be triplet.
It can be anything higher than a singlet, multiplet, anything you want. So let's go left to right. On the left side, the first molecule, how many signals do you see, first of all? 3, beautiful. Are they all singlets? No. Which one is the other multiplicity? Beautiful. So I forgot one hydrogen here, but these guys have only one neighbor. So they're the doublet. And then the multiplet is this guy. The very last ones, they're just singlets. So again, we have something higher than just a singlet. So that means that that molecule is showing spin-spin splitting. Okay, that's how you solve those questions. They look a little scary, but they're actually very, very simple. Okay. What about the molecule in the middle? Does it show spin-spin splitting? Why not? Because hopefully you guys notice that there's a plane of symmetry, meaning that they can be neighbors of each other. So you just have pure singlets. Okay. What about the last molecule on the right? How many signals do you see in total? I heard 2 or 3? 2. Beautiful. Do they show spin-spin splitting? You guys are absolutely correct because they are both just singlets. There's no neighbors to either side. Okay. Questions on that? Yes. Because basically to solve any questions like this, you have to find the multiplicity for all of the signals you see in there. So remember, before we even find multiplicity, we need to know the number of signals. In this case, as soon as we see a plane of symmetry, they're the same exact signal. If we want to do multiplicity, okay, I grab 1 bond away, carbon, 2 bonds away, carbon, 3 bonds away. I touch those 2 hydrogens, but because of the plane of symmetry, they're the same signal. So hydrogens of the same signal, they can be neighbors of each other. Okay, that's why it's so relevant in this case. Okay, we had any other questions on those 3 guys? Okay, we're good. So far, how are you feeling with normal multiplicity? Pretty good? Okay. No, bro. Okay, so let's make it a little harder. Let's talk about complex multiplicity. We don't want, we didn't understand it at all.
You want like.
Explaining the concept behind complex multiplicity, it's a little tricky, but it's
Okay.
complex, yeah, as it says in the name. But you don't have to worry that much about the definition. Okay, you just have to see it in practice, but most likely you're just gonna get 1 to 2 questions on complex multiplicity. Okay. Excuse me. So, complex multiplicity. First of all, let's look at a normal spectrum, okay? So in this case, that graph in there is showing 2 signals, the blue and the pink one. So, as you can see, we have a certain distance between the peaks between one signal, okay? The one that's showing the multiplicity. So those guys, we're gonna call them the J values, okay? Now, when we were doing normal multiplicity, the distances between each of those little guys in here, they're the same exact one. So let's say that they were all of them 2, okay? It's the same exact number, the same exact distance. But what happens with complex multiplicity is that the numbers in here, they're not going to be equal to each other, okay? So in this case, you can see that the signals are labeled JAB. This is not the best example, but let's say that we had another signal, JBC. So whenever it's normal multiplicity, J values are equal to each other. But if it's complex multiplicity, they're not equal to each other. Okay, yes. Thank you, yes. There is no question, so hopefully there was no one screaming in this recording, because generally we could not hear you, but the volume's up. So if you were screaming, I apologize for that. Just write something on the chat. So either way. Now, that's basically the gist behind complex multiplicity versus normal multiplicity, all about the J value. Now, for complex multiplicity, we're not just gonna say that, oh, this signal is a triplet. It's gonna be a little bit more wordy. It's gonna be a doublet of doublets. It's always gonna be 2 multiplicities paired together, okay? So the ones that you see in here, those guys are just some of the examples. Now, do you actually have to know how to name those guys? No. Okay. Now, we're gonna come back to this guy in here. But, okay, we know the gist behind it. But one of the questions that he might ask you is to give you to give the approximate J value for the relationship between 2 hydrogens. So usually this question is going to be phrased with a little chair that I know that a lot of you probably didn't like from Morgo 1, but it's going to be something similar to this, HA and HB. The same type of questions that you would see for like, what's the relationship between those 2 hydrogens, an antitopic, homotopic, those guys. But this time they can ask you about J values. Now, hopefully you guys remember that in a chair, we have axial and equatorial positions. Axial is just pointing straight up or straight down. Equatorial, they're tilted, okay? Now, you're gonna see that between HA and HB, there's a degree between them. So they're just straight from each other, so it's gonna be about 180 degrees away. Now, technically, you can use the Karplus curve, which is this guy on here, that he might have mentioned in lecture. Now, is this going to be provided for your exam? Absolutely not. It's not provided for the exam. So that's why I made a little list in here for you guys to memorize certain values. But as we saw in previous semesters, sometimes the values in here, they're not going to be the right answers. Why? Because your professor is, for the past few semesters, he tends to focus more on the Karplus curve. So what I would recommend you to do is to memorize 3 key positions. So first of all, 0 degrees, okay? That's the easiest one. Then let's look at 90 or 80, any of those guys, and then memorize the one for 180, okay? Because as long as you know those 3 key points, you could make a pretty educated guess on any other any other angles. But let's go back to our chair. we know that the relationship is 180 degrees away from each other. So you're gonna memorize your angles and then also the J values that correspond in here. So we know that 180 degrees corresponds to 10 hertz, which is the J value. Yes. 10, 14. I took this from your book. So
He said
14.
14 or 15.
Okay, then let's look at the graph that he gave you in lecture, not this one. I just took this from Orgo 1.
Like,
That's why J values are confusing for most students, because you're gonna see something in the Karpos curve and then he's gonna say an exception. So just for the sake of his lecture, it was 15 hertz or 14.
14 or 15. He said, okay.
Let's just say 14. That's a pretty solid number, yes. The one thing here? Yeah. Yes, exactly. Because remember, J values are just the little measurement between each of those peaks. So yes, you're absolutely correct. So again, this is just gonna be one question. So I wouldn't waste too much energy on memorizing the Karpos curve or all of the J values. Of course, if you can do it, more than welcome. It's one extra question, but so don't get too stressed out if you don't completely get it. Yes.
The values memorized were 0, 100.
0, 80.
0, around 80, and 180. Those are like the 3 key points of the graph.
Maybe not 90.
He said between.
Around there, yeah. So for simplicity, I'm just gonna give you the usual ranges that you might see for the different relationships. And I'm gonna tell you which is the one that he loves to test the most. So for equatorial, usually it's between 2 to 5 hertz. And yes, all of the J values are measured in hertz. Equatorial and axial, they're 4 to 6 hertz. Axial and axial, 11 to 14 hertz, which is probably why we saw that those two guys, since they were 180 degrees away from each other, there were also axial and axial. So that's where the 14 comes into play, yes. Around 60, yeah. Okay, now Bisinal, it's 6 to 8 hertz. And we are gonna highlight this one because he really likes to test this one. And also, we're gonna highlight the Geminal one. And the Geminal one is usually between 12 to 15 hertz. And then W coupling, 0 to 2 hertz. Now, W coupling just means that they're in completely different environments, so completely different signals. So let's say that it was HA with HD in here. Completely different signals, separate environments, so that's what it means. Let's just write completely different signals. Yes. So usually you use those terms whenever we were talking about double bonds, but they can also apply for single bonds, okay? So just in this case, I'm gonna be using a double bond. So this is my double bond, and if I'm looking at HA and HB in here, they are 1, 2, 3 bonds away, right? So that's gonna be a vicinal relationship whenever they're adjacent to each other. Yes, so vicinal, again, 1, 2, 3 bonds away, okay? They're just adjacent to each other, okay? That's the vicinal position. Now, for geminal, it's slightly different. Again, I'm using my double bond, but this time I'm looking at HC and HB. Those two guys are coming from the same carbon, from the same junction. So they're geminal to each other, okay? So any other questions on those, any of those terms? Now remember that we can use those terms as well for single bonds. Yes.
Just like the degree angle to the board, like we know axial was 180.
Here it's about 8 hertz.
That's like, for example, what would the degree be for like equatorial, axial, and then vicinal, terminal, like what would their angle?
Give me 1 second here. So let's just use this. 1 second, guys. Okay, so first of all, the numbers, the key points of the curve that I told you are right here in the little square. Okay, those are the 3 main values that you should remember if you want to memorize that Karplus curve. Now, if you ask your professor this, he's probably gonna answer, like if you ask him why the values are different between the established ranges and the Karplus curve, he's gonna say that it's usually just an average in rotation. Because remember, rotation, that happens with single bonds. Single bonds are constantly rotating, so there's not a specific angle all the time. Okay, so that's kind of like the logic behind why the numbers might be different. Okay. Okay, any other questions so far?
Seminal is bonds that comes directly from the same part.
Yes, vicinal, adjacent, geminal, same. And now, we cover one of the types of complex multiplicity questions that he might give you on the exam. But let's look at the other one. Are we ready to move on to the next one? Or do we need a few more minutes? Okay, you guys have to speak up for me to know. Questions?
What's the equals numbers? But like, I guess my question is, what are the equals for like each category? Like, what is the equal for vicinal?
Oh. Technically for vicinal, you could say that it's 180 degrees as well, because if we look at the drawing that I just did in here. So I wouldn't be completely comfortable answering that question because I don't want to give you the wrong information. So I would go to your professor in that case, or your TA. Okay. Okay. So now, the question that you see in here, it's about complex multiplicity. Okay, and this usually is going to be the most common question that you're going to see, not the J values. And again, it's just about 1 to 2 questions on this. So, okay, now, first of all, there's going to be a few key factors for you to notice that it's complex multiplicity instead of normal multiplicity. First of all, look at the answer choices. It's just numbers. We don't have singlet, quartet, any of those guys. So as soon as you see that, they're asking for multiplicity at any point and you see numbers in your answer choices, automatically complex multiplicity. Now, next factor is that they're telling you, they're saying this word specifically, theoretically. Okay, that's your next clue that it's complex multiplicity. And then remember that we were talking about J values. Whenever it's complex multiplicity, J values are not equal to each other, which we see it right there. So you have 3 different points that is telling you that, hey, you're doing complex multiplicity, not normal multiplicity. Okay, so to solve this one, first of all, let's look at our J values in here. So first of all, they're asking us for the multiplicity of signal B. So I'm just going to start by drawing out my hydrogens so it's easier to visualize everything. Little baby hydrogen and 1 and 2. Okay, again, I'm looking at signal B. I'm trying to find the multiplicity for the little hydrogen right in the middle. Now, whenever we get the J values are not equal to each other, we see that the adjacent signals are going to be signals A and signal C. So I'm going to be focusing on those 2. Now, what was the formula that we use for normal multiplicity again? N plus 1. So for complex multiplicity, it's going to be N plus 1 times N plus 1. Okay, it's time N plus 1. Now, you're going to have neighbors. You're going to have 2 different types of neighbors, and they're going to come from those letters that you see, and the J values are not equal to each other. So one of them is going to correspond for signal A. The other one is going to correspond for signal C. So in this case, for complex multiplicity, you're not going to be doing the 3 bonds away rule. What you're gonna do is just count the number of hydrogens per each of those adjacent signals. So let's see that we're looking at signal A. Signal A is composed of 1, 2, 3, 4, 5, and 6. So I'm just gonna plug in that number here, 6 plus 1. Then I repeat the same exact process with signal C. So for signal C, I have 1 and 2. So I'm just gonna plug in 2 plus 1. So 7 times 3, it gives you, what's the answer? Beautiful. And that's how you solve it, yes.
So we're not to be the bond, how we just.
You're just counting hydrogens per signal in the adjacent. So yes,
This, like molecule eligible, I don't know, not eligible, but like using compounds, like why can't you just use normal?
because it's told here that the J values are not equal to each other. Otherwise, just by looking at the molecule, you couldn't really tell. They need to specify that the J values are not equal to each other. Mhm. No, he does not make you do that. But in this case, the answer would be septet of triplets. Because we had a 7, so this guy, it's septet of triplets. Okay, okay, but again, he's not gonna be asking you to use those terms, but we're gonna continue our discussion on Wednesday. Remember, it's gonna be in this room. But if you have any questions, just let me know. I'm gonna stay a few minutes after aside. And then if you guys wanna join me to tutoring, come to the SLC with me. I'm gonna stay there for 2 hours. Yes. So that one, the whole molecule just has 6 signals because all of the hydrogens in here in the benzene group, they're grouped together. It doesn't mean that you have 6 hydrogens in here, or 6 signals in here in total. Mhm.
I was gonna. do the
Yes.
Okay, that I don't.
Yeah. Where's your class at? Going back that way?
Are you gonna look
Yeah, I'm gonna probably go get a toilet. I'm gonna see what I'm gonna go.